Great. I'm from Salo. I'll spend the next few minutes talking about a project we're working on called Fine Grain Application Driven Quality of Service for IP and 5G and next-gen networks. This is also known, depending on which presentation you listen to, as the semantically aware mission-oriented network framework. And what this framework does, it describes a fine-grained signaling mechanism between a host application and a network layer intelligence, which I occasionally call a network application. And this network intelligence may reside in IP or 5G or next-gen networks. So the fundamental argument is that applications should tell the network what they want, that they should be able to signal the network about its desires, and should do that on a fine-grained basis, potentially every packet. And conversely, networks ought to pay attention to this information. Oh, the signaling should occur by the application attaching what I call metadata to the packet.
Making it better, right?
That either request specific services or might reflect the packet's semantics, the semantics of the application data. And conversely, the networks also ought to be smarter, and they ought to respond to the application's needs and desires, and particularly they ought to listen to those metadata and respond to that metadata, use that metadata when they're processing a packet. So this framework describes a signaling mechanism, but doesn't really specify how it might be applied. Oh, the only idea here is that you have a signaling mechanism that really communicates with network intelligence. And it's not an end-to-end mechanism. It's really a mechanism to communicate between the host application and network intelligence, which I call in this slide network application. And the host has to generate both the metadata and the application data, and the network software in the host will munge that together and will insert that metadata into the packet header. So this metadata can be viewed as application signaling mechanism, application to network signaling mechanism that invokes intelligence in the network, and it may include parameters when it invokes that network intelligence, or it could be viewed as a description of the semantics of the user data that's contained in the packet, or it could be viewed as a request for special packet processing. Let me give you 3 examples. The first one's pretty trivial. The second one shows how that might be useful in 5G networks. And the third example starts to look at a more sophisticated use of this mechanism and starts to put real intelligence in the network. So as an initial example, trivial example, you might have a host that's streaming some sort of data, perhaps video data, using scalable video coding. That is, it breaks it up into a bunch of layers, and the base layer has the lowest resolution information, and then each successive layer has higher resolution data. Obviously, the base layer is what's most important. The higher level, higher resolution data is less important. And so then the application would indicate what coding level the data in that packet is a member of, and then network devices would use that information to prefer to discard the higher resolution data. In other words, the network is telling, the application is telling the network which packets are important, and the network is paying attention to that. And obviously, if that works, you have the application will experience a higher quality of experience because the network is throwing away the right things, the least important packets. More importantly, it observes or conforms to protocol layering. Rather than using signaling is used rather than deep packet inspection. So you get away from the idea that networks should be digging through application level protocols to figure out what's going on. Instead, just let the application tell the network what to do. And it easily integrates with the existing protocols. To jump ahead in the presentation, that this metadata could easily be transported in IPv6 hop-by-hop extension header. So there's no change to the IPv6 protocol. And this is a mechanism that might be good for responding to rapid network changes. Speaking of which, this is data that some of my colleagues collected. They had a 5G phone and walk around Minneapolis, and you can see that the network varies dramatically from 800 gigabits to, well, 0 in a very short period of time, and very rapidly, and often. And so this is just the sort of environment where you might want to avoid discarding important data. And so you could use the same sort of mechanism, again, using a layered coding scheme, and the radio access network could assign, for example, the low resolution, high priority packets to mid-band RF channels that are fairly reliable, but maybe not so fast. And then the enhancement resolution components could be shipped over millimeter wave RF channels. And so they are transmitted when you have a lot of bandwidth, and they aren't when you don't. And this, again, improves the quality of experience for the application of the user by assigning reliable channels to the important stuff, and high bandwidth, less reliable channels to the enhanced stuff. Now we step into an approach which starts to make use of this mechanism and starts to contradict the traditional smart host dumb network model. And I think it's time to re-examine that. So you could, we're working on it, you could use this metadata to implement a network layer publish subscribe service. Something is typically done at higher level layers. I think might be appropriate in some circumstances to do that at the network layer. So the metadata could contain the pub subtopic and some additional parameters, and then maybe an indication whether this is a published packet or a subscribed packet. And then the network would do all the work. It would maintain a list of subscribers and the topics, and do some sort of multicast tree sort of thing. So why would you want to do this? Well, and in what environments would you want to do this? It's certainly one opportunity to simplify end systems, and particularly low-end IoT devices, that they no longer have to do all this work. They just, if you will, just publish the packet, and all this other stuff happens magically behind the scenes, or rather at a lower level. And you could implement one good pub sub network layer service that could be used by a whole passel of higher level application protocols, or replace a whole series of application protocols. So you'd have one common protocol rather than having to re-implement this every time you had a new pub sub application. And I haven't said this explicitly, you may have noticed that the application layer protocols and data are opaque to the network layer still, right? No deep packet inspection, no examination of the application level data or the application level protocols. And so that means, among other things, that application layer data may be encrypted. The network doesn't care. And so you now have an opportunity to both provide intelligence in the service, provide intelligent services in the network, as well as to do it very securely. This also avoids overlay topologies. Oftentimes when you have application layer stuff trying to do things like this, they don't understand the current state of the network. They don't understand the current resources available. They don't understand the topology of the network, and they don't understand when those things changes. However, if you're doing this at the network layer, that network device has a lot more information about the current state of the network and can do a better job of, for example, figuring out how to multicast packets. And this may be a potential new service offering for network operators. Might be a new revenue source, might help lock in customers, which could be good or bad depending on which side you are on. You could extend this, the network could cache messages and provide a digital twin, perhaps. I think I've hit all the advantages of this architecture. We're implementing this in IPv6. The IPv6 hop-by-hop options header is a great use of this. And significantly, this requires no operating system level changes. That with a modern Linux kernel, an application can set the hop-by-hop extension header without any changes to the kernel. And we intend to demonstrate this with IPv6 and a freely available 5G network implementation. And at some point, we'd like to examine integrating this with programmable switches. With that, I am open to any questions you might have.